So for this part, right, by the time you hit this, you should already be, you should already know that this is what we'll call the general format of a quadratic equation. And you should be very, very familiar with this quadratic formula. And you should have no careless mistake in executing this quadratic formula to get the actual value of the roots. So as we move on from here, right, we are not concerned with the value of the x that you've gotten. So we are actually going to refocus our concern onto this part. So this part that is in your formula. So this part is has a special name, which we call the discriminant. So we're going to change the focus. We are not going to we are not concerned about finding the value of x. We are concerned about the value of the discriminant. Okay, so the value of the discriminant can help us to deduce the number of roots, and we also can have a visual idea of the graph. Okay, and also because of the discriminant, we can find certain unknown. So, okay, so I'm going to show you the idea. So if you look under this column, the equation column, it will be something that you know how to do. Okay, so I'm quite sure you should be very familiar with this already. So right now, I want you to look at the value of the discriminant. So this is the value of the discriminant. So do you realize in this situation, we actually got two value of answers. So we got two values of x. So these two values of x correspond to a positive discriminant. So in a way, right, our understanding will be when the discriminant is positive, okay, we have two solutions for x. We have two roots. And these two roots, right, we will describe the nature. So when there are two roots, we will have a special name for these two roots. So we will say that the nature of these roots will be real and equal. Sorry, it's not real and equal. It's real and distinct. So we use the proper word to describe the nature. So when the discriminant is positive, as you can see from the example, the discriminant is a value of 12. 12 is a positive value, and we end up getting 2x. So we realize that from here, when the discriminant is positive, we actually got two roots, and the correct words to describe the nature will be real and distinct. So in terms of graphical idea, it will look like this. Okay, so this one is very obvious that this is a small graph. So in terms of the graphical idea, right, where are the two roots? So the two roots are actually sitting on the x-axis. So this will be where the two roots are. So this is an important relationship because after that, we're going to use this relationship, we're going to understand this nature, and we're going to work backwards to find certain unknown. Okay, so in the next situation, okay, if you work out like as if you, in the normal way, you realize that now the discriminant is 0. So when the discriminant is 0, we realize that the supposedly two roots are the same. So essentially, right, there's only one root. Supposedly there should be two answers, right? But the two answers happen to be the same. So when the discriminant is equal to 0, we end up only having one root. So the correct way that we will describe the nature will be real and equal. So this is the words, real and equal. So the two roots, there's supposed to be two roots, but the two roots happen to be equal. So essentially, we only got one root. Root refers to the answer. So if I do it on a graphical way, it became something like this. So this will be the root. So in fact, right, later on you're going to learn a certain word. So in this case, right, we will say that the graph is tangent to the x-axis. So the idea of tangent is you are just touching. So when you touch, that means it's equivalent to one root. So later on we'll come to this wording in the further theory of this. So far we deduce from the value of the discriminant the number of roots, and we got the particular words to describe the nature of roots. So in the next example, we do like how we usually solve, and you realize that the discriminant is actually negative. And we are not able to get the answer because when you take a square root on -4, you actually get the math error. So in this situation, right, we realize that when the discriminant is a negative value, okay, -4 is a negative value. So we actually end up with no roots. We got no roots at all because we are not able to get any answers out of the formula. So in this case, right, we will describe the nature as unreal roots. So when you don't have roots, right, we can call it unreal, or we can call it imaginary, or we can, I think this, there can be other words, or sometimes we'll just say no real roots. So graphically, no real roots, right, well, essentially means this. It means that the graph doesn't touch the x-axis, it doesn't cut at all. So if you look at the graph, right, the graph essentially is entirely above the x-axis. So when it is above the x-axis, it doesn't cut the x-axis at all. So that's why you end up having no roots. So these are the fundamental idea. So with this fundamental idea, if your concept of this is very good, you can answer a lot of questions. So in this section, we are not concerned about the value of the roots. So the value of the roots, we leave it to e-math. So that is the accuracy of how you execute the formula. So right now, we are going on to the theoretical part. The theoretical part lies with the value of the discriminant. From the value of the discriminant, we know the number of roots, and we can actually describe them with some proper words. And we can be answering questions that deals with this concept. So I'm going to roughly show you, and your job is to see whether you can answer the rest of the question that follow. Okay, so before I show you, okay, let's do a quick summary first. So I am not concerned about the value of the roots. I'm concerned about how many roots are there. I'm concerned about the number of roots, which I can lead to the nature of roots. And we are going to do that by calculating the value of the discriminant. So our discriminant is known as b squared minus 4ac. So far in this, the three examples that I showed you. So back to the first example. So when the discriminant is positive, so discriminant is positive, we actually got two roots. We actually got two roots, and this is the nature of the roots. So the two roots can come from a smile graph, or it can come from a set face graph. So it depends, but it doesn't matter. The two roots are kind of sitting on the x-axis. So the description, right, if you visually see the description, the graph is going to intersect the x-axis at 2 points. Okay, and just now we also have an example where the discriminant is equal to 0. So if you go back to that example, you realize that the two roots happen to be the same. So that's why the nature will be known as the real and equal roots. So when we say real and equal roots, right, you either get a smile graph touching the x-axis, or you got a set face graph that's touching the x-axis. And in the third example, we got negative discriminant. Our discriminant is negative. Then we end up no solution. So no solution is known as no real roots. So graphically, the whole smile graph is above the x-axis. So there's no intersection at all. So the graph doesn't cut the x-axis at all. Or if you come to a smile graph, the smile graph is entirely below the x-axis. Whatever is it, you end up with no intersection with the x-axis. So this is a very conceptual thing. There's only 3 situations, but how good you are depends on your theory on the discriminant. So I repeat, we are not concerned about the value of the roots. We are concerned about the nature of the roots, which we can deduce it from the discriminant. Or it can be other way around. From the discriminant, we can deduce a number of roots. So there will be proving question, there will be explanation question, or there can be calculation question. So this is the main theory. Okay, it's a very, very simple theory, but a lot of people, they will just get lost in this whole topic. So read through the theory first before we look at some of the examples.